So the President of the United States just announced a major new scientific initiative, kind of on the scale of the Human Genome Project, which has been so far the largest initiative and greatest scientific achievement of my lifetime, is to see the human genome sequenced. And this new initiative, it's going to divert huge resources from the scientific community to this important project. The goal is to map the human brain, to map the function of the human brain, the pathways within the human brain, pathways that lead to diseases like schizophrenia, depression, memory, or associated with Alzheimer's. And so that's the goal. The goal is ultimately to create some sort of a map like this that allows us to see the pathways that lead to diseases or make people smart or have effects like that. So as I looked at all the news articles that were pouring out about this, it made me wonder, what would it take to see inside the brain? Now, ultimately, the picture that is developed will come from different new imaging methods that allow you to see inside the brain, and probably a lot of modeling, computer modeling, to put those pieces of information together. And so let's talk about what it would take to look inside the human body and see something going on. And so I thought I'd put together, just on one diagram, a picture to help you see what does it mean to see inside of human tissue. So of course, if you wanted to see inside of my arm, you couldn't see inside my arm. But all you see is skin and flesh. And that's because my skin is not transparent to light. The light bounces right off, is reflected, and so you can't see what's going on inside. And so if you look at the different types of spectroscopy that we've been talking about in this class, also in Chem 1, general chemistry, you spent a great deal of time in general chemistry using UV vis spectroscopy. You did things with Beer's law. Well, Beer's law still applies to IR and other types of spectroscopy. But you put solutions in little cuvettes and you measured how much light that was absorbed. If I stretch out the electromagnetic spectrum, and this is just a small fraction of the electromagnetic spectrum, you can see that starting down here at about 200 to 800, that's where you did UV vis spectroscopy as a freshman taking some sort of a first-year chemistry class. And there's a lot of stuff that absorbs. You never did any spectroscopy, any UV vis below 200, because even water absorbs pretty strongly there. You were typically doing UV vis spectroscopy in this region where you can see organic compounds. So water absorbs strongly there. We're not going to see anything in the brain below 200 nanometers. The water would simply absorb all the light. From 200 to 800 nanometers, that UV vis range, you still can't use light very effectively. A little bit, but not very effectively to see inside the brain. So the first problem is your skin contains a material called melanin that is very good at absorbing light. Light never passes through my skin. That's the purpose of the melanin in the skin. That's what makes skin have brownish hues associated with it. So all this melanin absorbs light very effectively at every single wavelength pretty much. And even if you stripped off my skin or stuck some sort of probe underneath my skin, the problem is that there's blood in there, and blood contains hemoglobin. That's probably the most prominent chromophore. You know, at some wavelengths, it's much more strongly absorbing than others. And of course, that's red, and it's a strong absorber. And so you have lots of blood that will also prevent you from visualizing. We've also talked in this class about IR spectroscopy, and that's way out over here. And you notice I'm using two different units. UV vis spectroscopists use nanometers to measure wavelength. And you might recall we measure IR spectra using frequency, using this inverse centimeters wave numbers types of units. And I've kind of plotted with those units here so you can see how that fits in with UV vis spectroscopy. And all kinds of stuff, especially water, absorbs in this region. That's why we never take IR spectra in water. We never use water as a solvent for IR spectroscopy because it would absorb too much light. But down here in this region between UV vis and between IR spectroscopy, this is called the near IR region. And if you look here in this little valley, this region right here is the most transparent region of the spectrum. Typical organic compounds don't absorb in that region. And so if you could design small molecule probes that absorb, you could see where those probes are inside the human body. If you were a jellyfish, if you had some sort of special viewing ability, and you could see in this region that has the best transparency, where few things absorb, If you could see it, at those wavelengths, I would look like a jellyfish to you. I would be transparent. The light would pass inside, go right through me. You could stand on the other side. So chemists are actively now trying to design organic molecules that absorb light effectively in this region, because you could use those as probes and tags to put inside the brain, to put inside the body, and watch where they're going. And the light would pass right through human tissue very effectively. Okay, so this was during your first year of general chemistry. Now we're talking about IR spectroscopy, and now we're totally going to switch gears and talk about a completely different type of spectroscopy in the class. Wow. Okay, I don't know how to turn that down, unfortunately. Actually, that was fantastic. You're listening to an organic molecule right now. This is an NMR. So when I was a graduate student and I used to take NMRs, I don't know if that's going to continue. I used to always run the NMR spectrometer with a little speaker on so I could hear my molecules each time, and I'll explain what that little pulse was about just momentarily. So I apologize for the volume on there, but maybe that'll help us wake up this morning. Okay, so chapter 14, we're starting a new type of spectroscopy. We spent a little time talking about spectrometry, and then we spent a whole lecture talking about IR spectroscopy, and hopefully you've been working all the problems in that chapter on IR spectroscopy. And now I want to talk about nuclear magnetic resonance spectroscopy. The fundamental idea here is the basis for MRI imaging, for magnetic resonance imaging. The word nuclear is in here. It has nothing to do with nuclear power or radiation, the kinds of radiation that come from nuclear power plants or nuclear bombs. This is based on radio frequency energy. Okay, so I want to start off by talking about what are we going to see if we use nuclear magnetic resonance spectroscopy. And what you see are atoms, and a specific property of atoms. And let's talk about what's required. In order to be able to see things with an NMR spectrometer, there's a fundamental requirement that those atoms must have a property called nuclear spin. And that's not a particular property of elements. It is a particular property of isotopes. So if I take an individual element, such as a hydrogen atom, there's multiple different isotopes. There's protons, there's deuterium, there's tritium, and they're not all visible by NMR. So in order to be visible by NMR, you have to have a property called spin. A particular isotope has to have a property called spin. And if you've got spin, there is a quantum number associated with you that will be non-zero. And so in order to see things, elements by NMR, to see isotopes by NMR, you have to have a non-zero spin quantum number. And the origin of that spin is because a spinning nucleus is like a tiny magnet. And so it has magnetic properties. When you put two nuclei that have spin together, those two tiny magnets can interact. When you put a nucleus with spin in a big magnetic field, it will interact with the magnetic field. So if we look at the common isotopes on organic molecules, carbon, hydrogen, nitrogen, oxygen, yes?
So the ones that have a nuclear spin, are they paramagnetic or diamagnetic?
I wouldn't call them diamagnetic. Maybe paramagnetic would be a better, I'm not even sure, I'm not enough of a physicist to answer whether paramagnetism is a good description of a nucleus. But it wouldn't be diamagnetic, that's for sure. Okay, so protons, the typical H's that you see attached to our organic molecules, those do have nuclear spin. And there's a specific spin quantum number associated with that, 1/2. Totally inconsequential to you. You don't need to worry about what the spin quantum number is for a proton. And most of the H's that you see attached to carbon, 99.98% of H's attached to carbon atoms in your body, in biology, in the floor, everywhere. Those are protons with no neutron in the nucleus. So you can very easily see those by NMR. And so that's the most common form of NMR that's used today is proton NMR, and that's what we're seeing. Now, a very small fraction of the H's that are attached to the molecules in your body are deuteriums. They have one extra neutron in the nucleus. Chemically, they behave exactly like protons. All the reactions that you see, if you switched a proton with a deuterium, the reactions would work in the same way. So the problem is that deuterium is not very abundant. And so because deuterium is not very abundant, you could see them by NMR if you jacked up the power on the NMR to see that tiny amount of deuterium in there, but it's very infrequent. So generally, you don't worry about seeing deuterium by NMR. You could if you wanted to. Okay, carbon. You can't see the most common isotope of carbon. That's carbon-12. So if I look at all the organic molecules in your body, glucose, glyceraldehyde 3-phosphate, glucose 6-phosphate, citric acid, most of the carbons are totally invisible by NMR. You can't see them by NMR. Their nuclei don't have this property of spin. But there is an isotope of carbon that you can see by NMR that does have spin, and that's carbon-13. And the problem there, once again, although not to the extent of deuterium, is that it's not quite as abundant. Only 1 out of every 100 carbons is a C13. All the rest are carbon-12. They react the same. They do all the same reactions. You can't distinguish them by doing some kind of chemistry. So you can do NMR. It's not as sensitive. Let me put 2 checks here near proton because it's so sensitive. You can do carbon NMR, but you've got to, again, jack up the power in order to see the tiny amounts of carbon that are there, because on average, so few carbons are actually C13. And all these other elements that are important, well, I guess there's only 2 other ones that have principal importance. That's oxygen 16 and nitrogen. Those are not, and N14, those are not NMR active. So we're not going to look at oxygen. You couldn't even see them. You can't see the oxygens and nitrogens on molecules by NMR. All we're going to see are carbons and hydrogens. So for the next 2-3 lectures, we're going to talk about proton NMR and carbon NMR. Those are the types of NMR that are useful to chemists. Whoa, oh, yes. Sorry, thank you for clarifying that. Yeah, I meant to put a scratch through there. So nitrogen, invisible. Oxygen, invisible. Even if you could have 50 oxygens on a molecule, totally invisible by NMR. Okay, I've shown you a picture here of an NMR spectrometer. In the basement over here of Reines Hall, we've got a huge room with 3-4 big spectrometers, much larger than this one. This is a smaller spectrometer. And inside of this, the spectrometer is basically a big tank. And inside that tank, there's liquid nitrogen that's extremely cold. I don't remember the temperature, something like minus 200 degrees. And inside that liquid nitrogen, there is liquid helium, 4 degrees Kelvin. And the liquid helium is used to cool down this superconducting copper coil right there. That's a bundle of copper wire, and they start this electricity running through that coil of copper wire and then take the electricity away, and because it's so cold, the copper is superconducting, and the electrons will flow infinitely around that tube, creating a superconducting magnetic field. So whenever you have a current running through a coiled wire, it creates a magnetic field, and I've drawn the magnetic field lines for you here so you can get a sense that right through the center of this NMR magnet, you've got this super duper duper massive magnetic field. Over each of our NMRs, we've got these planters out in the area between the buildings, so you don't drive your car over there and disturb the field or walk over that with your pacemaker and end up dying. So if you want to know where our NMR magnets are, they're right below those planters in front of Reines Hall. Okay, so that's an NMR spectrometer, and normally they're not cut open. This guy's, I'm not sure why he cut that open. It must be broken in some way. So I brought with you a picture of a tube with an NMR sample, and this is the way we put our samples inside that NMR magnet, and you can see here there's a little bit of liquid in here, and it's got a deuterated solvent in there, and we drop that sample down the center of this tube, and it sits on a cushion of air that keeps it right in the center where the magnetic field is super powerful. So that's the way we do NMR. You dissolve some of your sample, you put it in a tube, you drop it down the center of the NMR magnet, and then it sits there in the magnetic field. Now you can't use just any old solvent to do NMR. And I don't know if you can see this because it's not focused very well. We have special solvents, and boy, this is so, I can't even see if this is focused. But if I try to focus on this bottle, what you'd be able to read right here is that this is chloroform D. There's no protons. This is chloroform, CHCl3, but they've taken off the H and they put on a deuterium. You don't want to put a solvent with protons in an NMR magnet because then all the protons in the solvent will absorb all the signal. So we use deuterated solvents with deuteriums for NMR, almost exclusively. Okay, so that's NMR. It's a big magnet.
How much does one cost?
So somebody's asked how much the NMR costs, and it depends on what size you're buying. How much does a car cost? Depends on what car you buy. And generally it's the size of the magnetic field that makes all the difference. So they can cost anywhere from $100,000 for a superconducting NMR to $2 million, depending on the size. So we have a multi-million NMR magnet over on the side of Natural Sciences 1 that's vastly bigger than the ones we have over here near Reines Hall that's used for looking at things like proteins. Okay, so what's going on inside that, deep inside that NMR magnet when you drop your sample in? Okay, so you drop your sample inside of that NMR magnet, and there's this massive, massive magnetic field. And you need a massive magnetic field. That's absolutely essential for the experiment. So inside that supermassive magnetic field, the whole point, so let's just imagine that we have this supermassive magnetic field, and I'm symbolizing that with this shaded arrow here labeled NMR magnetic field. So surrounding your molecules on every side, they're sitting in this super powerful magnetic field. And I already told you that a proton is like a tiny magnet. That proton knows one of two things. It is either aligned with the magnetic field or it is misaligned with the magnetic field. Those are two distinct choices, and they are quantized choices. It doesn't matter if they're sideways or left or right. There's two choices, aligned or not aligned. And one of those is better than the other. It is better to be aligned with the magnetic field, and I'll just write aligned with. If you're aligned with the magnetic field, you're happy as a tiny little proton magnet. That's a good state to be in. It's an energetically stable state. But the alternative is that you can be aligned against the magnetic field. And again, this is where quantization of states is so mind-bending. It's like, well, what happens if they're halfway aligned? No, don't go there. Right? It's quantized. You're aligned with or you're aligned against, and those are the only two choices. And the more powerful your magnetic field is, the more stark those two choices are. So we always try to have the most powerful magnetic fields possible. So there's a good state that's stable, that's aligned with the field. And then there's this other state that is not as stable, that's higher in energy, where you're aligned against the magnetic field. And the point is that you can transition between these two things with energy. So in other words, if you absorb a photon of just the right energy, so E is equal to H nu. With just the right energy, you can flip the spin so it's misaligned. So it's aligned against the magnetic field. If you add just the right energy that is perfectly matched. If you put in the wrong energy, you won't flip that spin. And that proton will sit there and sit there and sit there, and eventually it'll jostle around with other molecules. And then eventually it will spontaneously revert back to the other spin state. And when it does that, it will emit energy at exactly the same frequency that it absorbed energy. And this is the basis of the NMR experiment. At the beginning of the lecture, I played for you this sound. And I don't know if I can go back to that. I'll try to take this thing off the screen for a moment so you can hear that sound in all of its glory again. You're listening to an NMR experiment. What's happening is the NMR spectrometer pulses the sample, and then the spectrometer listens. And it's listening for all the protons in the sample to start giving back their energies at their particular frequencies. So let's listen to a collection of molecules giving back their energy. You're listening to protons giving back radio frequency energy. You don't hear the spectrometer when it pulses because I've taken those sounds out. It would deafen you. But you're listening to the protons giving back their sounds. And if you're a musician or a sound person, you'll notice there's beats in there. That's a function of having two different frequencies that are interfering with each other. That means there's going to be two peaks in that NMR spectrum, two frequencies that you're hearing that are interfering with each other. Okay, so that's the NMR experiment. We drop our tube in the spectrometer, we pulse it with energy, the spectrometer listens to the frequencies, and then it plots those frequencies for you. Yes, question?
The sound that you have, the frequency is basically the same frequency as the one that you have in energy, right?
Well, when you pulse with energy, you're pulsing every possible wavelength at the same time. You can't just pulse with one frequency. You pulse with this loud sound that's exciting every single possible frequency. And then the protons all start spontaneously emitting back their sound. Okay, so here's a plot of frequency. Here's a plot of nuclei and frequency. If I had some organic molecule, and I've just drawn a random organic molecule here, this aldehyde with 2 chlorines on there. So if you were to plot all the protons and all the carbons giving back their energy, their radio frequency energy, on one plot, it would be the most useless plot in the universe. And that is because protons absorb and emit energy in a completely different region of the radio frequency spectrum from carbons. In order to fit all of this on one plot, you'd have to scrunch down all the proton peaks so small that you couldn't even distinguish them. And the same thing with carbons, except it's worse with carbons because there's so few carbons that the signals aren't very big. So nobody ever plots carbons and protons on the same spectrum. We always do those separately. We blast with radio frequency energy over here, and then listen over here, and then plot over here to see protons. And when we're interested in carbon NMR, we blast with energy over here, and then we listen, and we just plot this region individually. So from now on, I'm going to separate proton NMR from carbon NMR. We do those as two separate experiments because you just can't fit those onto the same plot. So, and so for the rest of these lectures, I'm going to separately discuss C13, carbon-13 NMR, and proton NMR, even though the basis of the experiment, pulse with energy and listen, the basis of that experiment is the same. There's no difference there. Okay, I want to come back to this thing that I kind of skipped just a moment ago about NMRs, about the physical NMR instrument. Because there's an important point that I meant to make that I'm realizing that I forgot. And it's essential for your understanding of why spectra have all these weird labels on them. So here's our NMR spectrometer that I showed you just a moment ago. It's that same slide. And the point that I wanted to make is when you order a brand new shiny NMR, you pay $200,000, $300,000, your NMR arrives. It's just come from the factory. They've just finished wrapping all the coils and packaging it up, and you fill it with liquid helium and liquid nitrogen. The problem is that nobody really knows exactly what that magnetic field strength is going to be until they boot up the magnet. And that's the point. When they first boot it up that they realize, oh, now we can finally measure the magnetic field of this custom-built superconducting magnet that we have created. And no two NMR spectrometers have exactly the same magnetic field. And that's a problem. It is a problem that no two magnets, no two big $200,000 magnets, even if the manufacturers feel like they made them exactly the same way, will have exactly the same magnetic field. And so let's see how that creates complications for the NMR experiment and how the community has had to deal with them and why you're never going to see a spectrum that uses frequency for the x-axis. Yes?
Is there a reason why it doesn't, two spectrometers don't feel the same?
So the question is there a reason why spectrometers don't have exactly the same frequency? I'm sure it's an engineering issue, and I'm not competent to comment on why they can't make them exactly the same. Okay, so let me give you an example of a sample. This is chloroacetaldehyde here. And let's imagine I go to my lab. I'm sure we have chloroacetaldehyde in my lab. If I make up some sample in an NMR tube and I pop it into a spectrometer, And let's suppose this is just a thinking experiment that my spectrometer is operating with a magnet with a 9.4 Tesla magnetic field. And then I ask my friend, I call over to Hamburg, Germany, and I say, hey, could you prep up a sample over there in Germany of chloroacetaldehyde and drop it into your spectrometer? The problem is they won't have exactly the same spectrometer. Maybe their spectrometer is operating with a magnetic field strength of 10.3 Tesla. Right? And it becomes a problem if our NMR magnets don't have exactly the same field strength. Because if they don't have exactly the same field strength, common molecules will not resonate, will not absorb and emit energy at the same frequency. So we won't get the same spectrum. So for example, tetramethylsilane, this is very commonly used in NMR spectroscopy, will have a different absorption and emission frequency. My chloroacetaldehyde, the 2 carbons in there, I might see that absorbing at 100,000,000,3,800 hertz, whereas my friend in Germany will see that same carbon over here absorbing and emitting at 100,571, whatever, 100 million, at a different frequency is the important point. All our frequencies will be different. Now, how are we going to publish our data and have any 2 people tell that they've made the same molecules? And so here's what we do. Here's what the community has decided to do to make all this work out. What we've decided to do is we've decided to have everybody measure their frequencies relative to one molecule, and that's this molecule tetramethylsilane. It's volatile, so if you add a few drops to your sample, when you evaporate off the solvent, the tetramethylsilane comes off. The chemical, the frequency at which this absorbs and emits is much lower than the frequencies for most other molecules. So almost always, all the other peaks will be on the left-hand side here of the tetramethylsilane. And you're not seeing the silicon. I'm sorry. You're actually seeing the carbon atoms. That's what I mean to point at. Now, here's the important point. If I've got a magnet that's 10% stronger in Hamburg than in Irvine, then all the frequencies will be 10% larger. So if I can just divide by that 110% to normalize things, if I could just squeeze that spectrum or stretch the other spectrum, everything will overlay perfectly. If you adjust for the magnetic field strength, everything will overlay perfectly. So we don't plot spectra in hertz in frequency. What we plot is in parts per million. Everybody has agreed that they're going to squeeze or stretch their spectra and plot out the frequencies in 571,000 parts out of every 100 million parts of hertz. So we list frequency using this symbol delta, and our units will be parts per million and not hertz. If you wanted, you could convert it back to hertz, but that wouldn't help you or anybody else. So we're never going to see hertz on that bottom axis. We use this sort of normalized version of frequency. And that's what allows, regardless of your NMR magnet, anywhere on the planet, as long as you take that into account, everybody's going to end up with the same spectrum. Everything is always measured relative to tetramethylsilane. Here's the carbons. That's the carbon atoms there in the tetramethylsilane at that little peak. Here's that carbon atom, and it doesn't matter whether it's Hamburg or Irvine or Boston, that's going to be absorbing and emitting at 48 parts per million. And over here, here's that carbonyl at 194 parts per million. That's the carbonyl carbon. Okay, so we're not going to see hertz, we're going to see parts per million. There's a second weird feature here because the spectroscopy is related to magnetic fields. And that is we add special labels to our spectra. And we describe this region over here, and you don't need to worry about why. We describe this region over here of the spectrum as downfield. Because in the old days, they didn't plot against frequency, they plotted against changing magnetic field. And you don't need to worry about why that is. It's just going to seem completely weird to you that I'm going to sometimes say, and I'm going to try to avoid it, but I know I'm going to slip. I'm sometimes going to say, see that carbon resonance downfield over there? And you're going to say, oh, down over, no, it's backwards. It's backwards, and I hate that. And it's going to screw you up, because when I say downfield, I mean at high parts per million. I didn't invent that, sorry. Okay, so downfield, when you hear me say downfield, I mean at high parts per million. The other term I'm going to use for this region of the spectrum is I'll refer to that as shielded. And I'll explain that later. Okay, so high parts per million, that's when I say downfield. Over here at this region of the spectrum at higher frequency, we're going to refer to this as upfield with low parts per million. And the other term that I'm going to use for this parts per million is chemical shift. This is a term that came from physicists who first realized that there was chemical information in these frequencies. You know, for me, everything is chemical, so it doesn't make sense to refer to this as chemical shift. But the physicists who first observed differences in carbon frequencies or proton frequencies were totally mystified. They said, oh, there's some shift. It's a chemical effect. So I'll still refer to that as chemical shift. And this region down here at low parts per million, I'll sometimes refer to as de-shielded. And unfortunately, it takes quite a bit of time for you to get used to those terms because they're opposite. Okay, so we plot chemical shift in parts per million. We don't plot it in hertz. So I'm going to refer to our x-axis as chemical shift. It's measured in parts per million. And when I don't have space, I'm going to use the symbol delta for that. So I'll try to avoid this phrase downfield because I know it's so counterintuitive, and upfield, but if I slip, you're going to have to quickly process in your mind what that means. Oh, my word. Oh, no. Okay. Doesn't matter, I'll manufacture my... So my intention here was to draw two spectra for you, and I'm realizing that it plotted in such a light gray that even I can't see what's underneath here. This is two NMR spectra of this molecule. Of this dibromopropane. You could have made this dibromopropane molecule here by, let me just make sure I've got this thing focused. You could have made this dibromopropane molecule by brominating a double bond. Doesn't matter how you got it. If I put this into a little sample tube and drop it into the NMR spectrometer and take a C13 spectrum, it will look beautifully simple and satisfying. There's 3 carbons in dibromopropane. When I look at my carbon-13 spectrum, here it is. Here's my chemical shift. It's measured in parts per million delta. I'll see exactly 3 peaks. Oh, that's wonderful. It's simple and it's easy. If I then switch the spectrometer or type a new command into the spectrometer and say, okay, now show me the proton NMR spectrum, what I'll see will be unfortunately, a mess. It'll have stuff that looks like this, some other peaks here, and some other peaks here. You're going to have so many peaks. There will be 16 peaks in the proton NMR spectrum for this molecule. 16. How do you get 16 peaks? There's not even 16 protons in here. There's only 6 protons. Look at the molecular formula. Proton NMR is vastly complex relative to carbon NMR. There's no one-to-one correspondence between the number of peaks that you see and the number of protons in a sample. Carbon NMR is simple because there is a one-to-one correspondence between types of protons and carbon resonances. So I'm going to skip ahead in the chapter, and I'm going to start explaining carbon NMR to you because it is simple and it is powerful for you. And then when we're done with that, we'll talk about the complex stuff. And we'll talk about why there's so many peaks in the proton NMR spectrum. So once you've used proton NMR for a couple of years, you'll love the complexity of proton NMR because it gives you extra information. But when you're sitting down taking your exam, you're going to say, that sucks. That complexity sucks, right? Complexity, because you haven't yet spent 2 years looking at spectra. Yes?
So for the carbon NMR, how can we get any peaks? Is it that only 1% of the carbon is
Well, when I put sample inside of a tube, I'm putting close to 6.02 times 10 to the 23rd molecules in it, right? Right? You're not putting just one molecule in a tube. You're putting, I don't know, bazillions of molecules. So there's lots of carbon atoms. And yeah, there's no way to measure spectroscopy on a single molecule. The amount of stuff, even a drop of sample in an NMR tube is zillions of molecules. Okay, so so the first and the most powerful thing that you can do when you're trying to analyze NMR spectra. The most powerful thing that you can do is to try to gauge how many different signals should I expect to see in my carbon-13 spectrum. Right? This is the simplest way for you to tell, does my spectrum match this structure? Or does my structure match this spectrum? The simplest and most powerful thing that you can do is to try to figure out ahead of time, well, once I look at the structure, how many signals do I expect to see? And so the fundamental rule here is that carbons that are chemically equivalent due to symmetry give one peak. And so let's talk about the effect of symmetry. In other words, if two carbon atoms experience exactly the same environment and are chemically equivalent, if they would react chemically in the same way, then we should expect them to absorb and emit radio frequency energy in the same way. So let's start off as an example. What we're going to do here is a little exercise where we try to guess how many carbon peaks we should expect to see in a C13 spectrum. So I'm going to start over here and I'm going to label these carbons. Here's carbon 1, here's carbon 2, here's carbon 3, and here's carbon 4. And I can immediately tell that all 4 of those carbons are unique and distinctive. Carbon 1 is closest to oxygen. Carbon 2 is 1 carbon away from oxygen. Carbon 3 is 2 carbons separated from oxygen. Carbon 4 is at the other end of the molecule. All 4 of those are unique carbon atoms that experience different environments and couldn't possibly experience the same environment because they're separated by different numbers of bonds from that electronegative oxygen atom. I would expect to see 4 unique peaks in the carbon-13 NMR spectrum for that. I see 4 distinctive carbons. Now, to help you understand the issue of symmetry, let's take a look at this isomer of butanol. Instead of N-butanol, here's tert-butanol. And when I look at this, I see a carbon in the center here, this quaternary carbon. I'll call that carbon 1. And then I see a carbon sticking up, that's carbon 2. And that's 1 carbon away from the oxygen atom. And now there's 2 other carbon atoms here. And those 2 other carbon atoms are exactly like carbon 2. If I just gave this a quick flip around that carbon-oxygen bond, all those other carbon atoms, that's meant to be like a rotation arrow there. If I spun around that carbon-oxygen bond, what I would find is that all of these other carbons will be exactly the same as carbon 2. I'm simply going to label those as carbon 2. They're indistinguishable. There's no chemical reaction on the planet that would react with them in a different way. They're related by symmetry. There's no naming principle you can use that will allow you to name those differently. And so the carbon-13 NMR spectrum for this, I would expect to see only 2 peaks. I would expect to see a peak for the carbon directly attached to oxygen. And then these other 3 carbons that are 1 carbon away from the oxygen would also be at exactly the same. They would absorb radio frequency energy at the same frequency, and they would emit at the same frequency. Indistinguishable. So in other words, just by counting the number of peaks in the carbon NMR spectrum, I could immediately distinguish between those 2 molecules. And I don't need to know anything about what frequencies they're absorbing and emitting at. I just count the number of peaks. And that's easy to do. And I expect you to be able to do that. Okay, here's another compound. And let me start numbering. You could use letter A, B, C if you want. I'm going to continue to use my numbers. Carbon 1 here is directly attached to chlorine. Here's another carbon that has an H attached to it. It doesn't really matter that there's an H attached. That's different. It's 1 carbon away from chlorine. And then I've got 2 methyl groups. And these 2 methyl groups will be indistinguishable. If I flipped this around just right, there would be a plane of symmetry through this molecule. So carbon 3 over here is not distinguishable from carbon 3 or on the other side. Those are the same. They're the same by symmetry. They are symmetrical with each other. So I would expect only 3 signals for this chlorobutane molecule here. For this, it's actually 2-methyl, 1-chloropropane. But the bottom line is that those 2 carbons there are symmetrical and the same. I could spin around. Let me try to draw this other spin arrow. I don't have a very thin pen here, but if I spun around this bond, I could get those 2 carbon atoms to experience the same environment. Okay, let's take a look at a very similar looking molecule here. And I've got carbon 1 here, it's part of the alkene that's directly attached to the chlorine. And then up above that, I've got another carbon that has no chlorine attached. I could definitely distinguish those. But what's tricky here is that there's two methyl groups, and those are not the same. There's a methyl group over here that's on the same side of as the chlorine atom, that is cis to the chlorine. And then there's another methyl group, and it's different. It is trans to the chlorine. And you can't spin around that double bond to suddenly make it cis. Molecules don't do that. This methyl group on the other side is different from carbon 3. I'm going to label that carbon 4. One methyl group is cis to chlorine, the other methyl group is trans to chlorine. And they don't interchange. You'd have to spin around the double bond, and double bonds don't do that. So here I would expect 4 signals in my carbon NMR. And it's very easy. I could look at the carbon NMR and instantaneously, oh, 4 peaks. Maybe that's a match. Maybe it's not. But if I see 2 peaks in my carbon NMR, that's a pretty good indication that it's not the right molecule, that the spectrum doesn't match the molecule. Okay, so here's another, and I'm trying to make it look complex and fancy here to throw you off. So here I've got 2 carbons that are attached to the oxygen atom. I'll start labeling that one as 1. Carbon number 1 here has 2 H's attached. There's no other carbon like that in this molecule. Here's carbon number 2 that has a hydroxyl group attached. That's distinctive and unique. There's no other carbon that has a hydroxyl group attached. And then over here, carbon 3 has a methyl group sticking off of it. There's no other carbon like that. And then the 4th carbon in this structure is just a methyl group, and that's distinctive. This would exhibit 4 peaks in the carbon 13 spectrum. So I expect you to be able to work through this and identify how many peaks you would see in the C13 spectrum. Here's an aromatic compound, and I think it will help us if I draw the resonance structure of this. So let me start off by taking these double bonds, and I'll draw, and we're going to do a lot more resonance structure drawing in upcoming chapters. But when I draw the resonance structure for this, the point is you can't just look at the positions of the double bonds and decide. This is an equivalent representation, this resonance structure up here. This is an equivalent representation of this dichlorobenzene molecule. It's exactly equal. And the important point is, if I start numbering my carbons, sorry, that was supposed to be an alcohol, so chlorophenol is the name of this molecule. Okay, if I start numbering my unique carbon atoms, I'm going to label the carbon that's next to the hydroxyl group as carbon 1. And then when I walk 1 carbon over, there's 2 different carbons that are 1 carbon away from the hydroxyl. And they're identical. And you can't use the positions of the double bonds to tell you whether they're the same or different, because when I draw the resonance structure, now the carbon 2 up above here is double bonded. And so you have to keep that resonance in mind to understand the equivalency of carbons 2 and 2. Now when I walk 1 carbon further over, I've got 2 of those as well. Those are identical by symmetry. And then finally, when I look at the last carbon that's next to the chlorine atom, there's only 1 of those. So by NMR, because of the equivalence of carbon 2 and 2 and carbon 3 and 3, they won't give different peaks. Carbon 2 and 2 will absorb and emit at the same frequency, and carbon 3 and 3 will absorb and emit at the same frequency. And so I expect only 4 peaks in the carbon 13 spectrum for this molecule. Okay, so that seems kind of abstract, so let's take a look at our first NMR spectrum. It's a carbon NMR spectrum, and let's try to interpret this. And this is typically the situation you're in. I find all the books tend to make up stupid problems like this that have no basis in reality. I'm walking into the lab and I find this mysterious bottle just sitting there that's labeled C2H4Cl2, and I don't know what it is. Here's the C13 NMR spectrum. You tell me which one of these 2 molecules it is. Now, nobody just walks into their lab and finds mysterious bottles like that, but usually you make things and you're not sure what you made. You synthesize them or you isolate them from nature. Okay, so the first thing you should do is notice I see 2 peaks in my C13 spectrum. And you have to figure out, maybe both of these chemical structures should exhibit 2 peaks. But at least we can ask, how many peaks do you expect to see? So I'm going to start over here with this 1,1-dichloroethane over here. And I see that this carbon over here has 2 chlorines attached. I'll call that carbon 1. And then I see a carbon that has no chlorines attached. That's definitely different. There's no way that the carbon with 2 chlorines should absorb and emit at the same frequency as the carbon that has no chlorines. I expect 2 signals in the C13 spectrum for that. And look there, I've got 2 signals. But what about this other dichloroethane, 1,2-dichloroethane? I look over here at the left-handed carbon and it has 1 chlorine attached. But then I look over here at the right-handed carbon and it also has 1 chlorine attached. I look over here at the left-handed carbon and it's 1 carbon away from a second chlorine. Well, so is this right-handed carbon. There is nothing you could do to distinguish between these 2 carbon atoms. That 1,2-dichloroethane will give exactly 1 peak in the carbon NMR spectrum. Those 2 carbons are indistinguishable. And the very fact that I see 2 peaks here in my carbon NMR spectrum has immediately resolved this issue. I immediately know it cannot be this, because that should give 1 peak. Whereas that should give 2 peaks. And I don't need to know anything about the frequency of absorption for that. It's very easy to resolve that only one of those can possibly match. Okay, here's a set of 3 isomeric compounds. Let's just see how we can use this symmetry. And 3 spectra, let's try to match them up. Each one of those compounds matches with one of those 3 spectra. Let's see if you can predict how many signals you expect to see in the NMR spectrum. Okay, so let's start off up here in the top. How many different signals would you expect to see for top compound? Would somebody like to, it's not matched to the spectra on the side. Yeah, I'd expect to see 3. Excellent. So I come over here and I see there's a carbon that's attached to chlorine. Well, here's another one that's attached to chlorine. Exactly the same. Just flip over the molecule horizontally and you won't be able to tell the difference. Here's a carbon that's that's separated by 1 carbon from the chlorine atom. And on the other side, here's a symmetrically disposed carbon atom. Same deal. And then I come down over here and here's now a carbon that's far away from chlorine, and there's a carbon down there that's equally far away. You cannot tell the difference between these 2 carbon 3s by carbon NMR. Okay, let's take a look at this next molecule. And we'll ask, how many peaks do we expect to see for this next molecule in the C13 spectrum? How many different types of carbon atoms are there? So I see carbon over here that's attached to chlorine, and over here I see carbon that's attached to chlorine. Identical. And then I'll walk upstairs here and I'll see this carbon that's in between the 2 chlorine atoms. There's only 1 of those. That's unique. And then I'll go 1 farther away. Down here there's a carbon that's attached to carbon 1, so it's separated from the chlorine by 1 atom. Well, here's another one. I could say exactly the same thing about this. And then finally, there's only 1 carbon atom here. Sorry, I should put 3 for that, just to give different numbers. And then down at the bottom of this molecule, there's a single carbon atom that's as far away as it can possibly get, that's absolutely distinctive in terms of it has 1 H attached, it's 2 carbons separated from the chlorine. So I expect to see 4 peaks. So this would have 3 peaks, and this would have 4 peaks. That's peaks. I'm not doing a good job of writing. Now I come down over here to this bottom molecule, and you can see the surprising effect of symmetry. I start numbering my carbons. Here's a carbon that's right next to chlorine, and down below there's one that's next to chlorine. It's the same. And then I come over here at 2 o'clock and I see a carbon that's 1 carbon separated away from a chlorine, but you could say the same thing for this other carbon on the other side. And when I walk down below, this carbon down below is also 1 carbon separated away from a chlorine. All 4 of these carbons on the side are indistinguishable. I would expect to see only 2 peaks in the NMR spectrum for this compound. Just by looking at the number of peaks in the carbon NMR spectrum, and by using my knowledge of symmetry, I can very quickly get a huge amount of information from a carbon spectrum. So I'm going to give you one last $1 million secret before we finish up here, and then I'll explain how to use the chemical shift to make sense of this. Here's a $1 million secret to help you interpret carbon NMR. And I'm giving it to you for free. So carbons that don't have attached hydrogens give small peaks. So when I look at these benzene rings, there's some carbons that have no hydrogens attached to them. They have chlorine atoms. And look at that. There's carbon 1. That peak right there has the chlorine. There's no H's attached. I look over here at this spectrum. Well, you'd have to match it up. That tiny peak there has a chlorine attached and no hydrogen. And then this last compound over here that has a carbon with no hydrogens attached and a chlorine, that's that small peak there. And you can use that to help you decipher spectra. Okay, so we'll pick up where we left off on Friday and then start talking about proton NMR.